This is section 2.7, tangents, velocities, and other rates of change. And our content objective 2 is to solve problems involving position and velocity. So what I want you to be able to do by the time we're done is discuss how you could decide whether you're finding a time, a velocity, or a position in a particle motion problem. And before we can do any examples, I want to remind you of what we did in section 2.1 that involved average velocity and instantaneous velocity. Remember that average velocity was a synonym for a secant slope on the position curve, whereas an instantaneous velocity was a synonym for an tangent slope on a position curve. And we can see this here as a distance traveled over a time elapsed. That was a y coordinate on the position curve's difference divided by a time coordinates differences on the position curve. And if we let those 2 points get closer and closer together, then we of course end up with that same tangent slope that we saw earlier in objective 1. So if we look at example 1 here, it says, suppose that a ball is dropped from the upper observation desk of the CN tower 50 meters above the ground, where the distance fallen s is given by s equals a function of time equals 4.9 t squared. And we have two parts to this problem. First is what's the velocity of the ball after 5 seconds, and then part B says how fast is the ball traveling when it hits the ground. So since I have two different times involved here, I'm probably going to want to do a generic slope and then just evaluate that generic slope at 5 and then again at the time when it hits the ground. So I'm going to do that first and then we'll see how it works. So maybe I'll even do that down here in our paper, just kind of the generic slope. And you can write that as well. If we go here, we're going to have a generic slope at our generic point a comma f of a. So remember that slope, instantaneous slope, which is the velocity at any time, or we should say at the time a, is going to be the limit as h approaches 0 of that time a plus an h plugged into the function minus the time plugged in at a over the difference between those two times, which is just h. If I plug a plus h into this function, I'm going to get a 4.9 times an a plus h squared. And if I plug an a in, I'll get a 4.9 times an a squared. And on the bottom, I'll still have an h. So if I multiply that out, I notice that I have this 4.9 showing up in both of them. So I'm actually going to factor that 4.9 out so I don't have to deal with it. And I'll be left with an a squared plus a 2ah plus an h squared. And then I have minus an a squared. So there again, we're seeing that things that don't have h's in them are disappearing off of the top. So I can get rid of that a squared, and then I'm left with something that I can factor. So I'll have a limit as h approaches 0 of a 4.9. I can pull an h out now, and I'll have a 2a plus an h remaining over an h. Now the h's cancel, and I can compute the limit because h equaling 0 is no longer a problem. And I'll get a 4.9 times a 2a or a 9.8a. So this now represents the velocity at any time t equals a. So if I want it after 5 seconds, I can just do a 9.8 times a 5, and I'll end up with a 49. And let's also keep in mind that we've got this function that's a 4.9 t squared that's measured in meters and seconds. So a slope on that curve is going to be a rise over a run, which is going to be a meters over a second. So we get a meters per second, which sounds an awful lot like a velocity. So we know we're in the right place. Part B says, how fast is the ball traveling when it hits the ground? So in order to compute this one, we know it's going to be 9.8 times whatever time is required to hit the ground. So in order to find that time, I need to solve for when the position function equals the full distance that has fallen. So that's at the 50-meter mark. So to do this, we can do it on our calculator using that solve feature, and we can type it in just like this. Now, before we do this, I want to point something out, that I have a t squared equaling something. So if I solve this analytically, I'm going to end up with a plus and a minus. And we know that time in this scenario is only going to be positive. So what I'm going to do is I'm going to restrict the solutions to values of t that are just greater than 0. And I'm going to show you how to do that on your calculator. So get your calculators out and turn them on. And let's remember that, that solve button is located under the algebra function. So I'm going to go to the F2 algebra, and I'm going to tell it to solve for when 4.9t squared equals the full 50 meters fallen. I'm going to tell the calculator that I need to solve for t. Then I'm going to close it. Now, normally if I hit enter right now, it's going to give me an exact value, and I'll get both the positive and the negative. So I only want to look at the positive one. So if we come here to this button right here, this says evaluated when or restricted to, and so we can hit that button and then tell it we only want t's to be positive. And if we look over here right above the decimal button, there's a greater than symbol that I can access using my second. So I can use greater than 0. Now again, if I hit enter, it's going to give me an exact value. It'll probably have some radicals in it. So I'm going to override my calculator's desire to do that by hitting diamond and then enter. We can see now that we got a time, and this is your first lesson on accuracy. On the AP exam, you cannot round values and then use them in subsequent computations. So what we want to do is we want to keep all of these digits when we multiply it by 9.8. We don't want to round until we're done. So how we can use our calculators to automate that process for us is we can say that we want to compute a 9.8 times a t, and then we can do such that and go grab that full t without having to write it down and possibly transpose numbers or write them incorrectly, and hit enter, and notice that we got the full, as many digits of accuracy as our calculator could provide us. So we're going to do 9.8 multiplied by the t when t equals the value we just found. And if we hit enter, we get a 31.30495. On the AP exam, all decimal approximations need to be accurate to 3 decimal places. So we can either truncate and do 31.304, or we can look to the 4th decimal and choose to round up. So I'm going to round up, and we'll have 3.19, what was that, 194? And we will end up with an answer of 31.305 meters per second. So we're done with this example, and we're ready for example 2. So example 2 says an equation for free fall on the surface of Mars is given to us as this position function where t is measured in seconds. Assume a rock is dropped from the top of a 200-meter cliff and find the velocity at t equals 1 second. Now in this particular case, I only have one time I need to worry about, so because there aren't 2 of them, I don't need to do the general slope. So I can just compute the velocity at 1 will be the limit as h approaches 0 of that position function at 1 plus h minus the position function at 1 over h. If I plug 1 plus h into that function, I end up with a 1.86 times a 1 plus h quantity squared, minus, if I plug a 1 in, I just get a 1.86. And on the bottom, I still have that h. h equaling 0 is an issue, so I better be able to fix it by multiplying out the top. If I do so, I can see that 1.86. I don't want to mess with it, so I'm just going to factor it out. I'll have a 1 plus a 2h plus an h squared minus a 1 if I factored it. Notice that everything on top that doesn't have an h in it disappears. So now I can factor out that h. And I'm left with a 2 plus an h inside. And the h's will cancel. So now if h goes to 0, I get a 1.86 times a 2, which is a 3.72 meters per second. With example 3, it says if an arrow is shot upward on the moon with a velocity of 58 meters per second, its height after t seconds will be given by this function. So the question is, when will the arrow hit the moon and what is its velocity at this time? So first we want to figure out when the arrow hits the moon. And when we're hitting the moon, are we given information about how fast it's traveling, where it is, or what the push on the rock is, or the arrow, excuse me. And what we should be able to answer is that when we hit the moon, we know the position is going to be 0, because the position is the height of the arrow from the base of the moon, or from the surface of the moon. So when the arrow hits the moon, let's say this is part A, when that arrow hits, we know we need to solve for when h of t equals 0. And then once we find that solution, whatever that t value is, then we're going to compute the slope, or the tangent slope, or the velocity at that time. So I suspect that this is going to be a big nasty decimal. So rather than computing our slope using the big nasty decimal, I want to find a generic slope at any time a, and then use that time by just plugging it in. So we'll let h go to 0 on the limit of h of little a plus h minus big H of a over little h. I'm going to plug in a plus h into this. Notice everywhere that there's a t, I'm going to plug an a plus h, and then I'm going to subtract this output when an a is plugged in. And that will all be divided by an h. H can't be equaling 0 because we'll divide by 0, so again we're going to have to simplify. Looks like I've got a 58a plus a 58h minus a nasty decimal, so I'm going to factor that out and see if maybe we can make things nicer on ourselves. That'll be an a squared plus a 2ah plus an h squared. And then I'm going to subtract a 58a and a 0.83a squared. And let's look and see what cancels. Notice everything that doesn't have an h in it should disappear. So there's the 58a. Here's the 0.83h or a squared. And it looks like we have left things that have h's in them. So we should be able to cancel that h out, and we'll get an h times a 58 minus a 0.83 times a 2a minus a 0.83 times an h, and that's it. And then on the bottom we have, let's get that parenthesis to match, and on the bottom we'll have that h, which will cancel. So now if I let h go to 0, I'm left with a 58 minus a 0.83 times a 2a, so that's a 1.66a. So here's my general formula for the velocity at any time a, and we're going to use it at the time when the arrow hits the moon. So to find the time when the arrow hits the moon, I'm going to access my calculator. I'm going to turn it on. I'm going to hit my solve. I'm going to solve for when this h, which is 58t minus 0.83 t squared, equals 0, and I'm going to solve with respect to t. And then I only want to look for after the arrow has been shot upwards. So I'm not going to want to find that t equals 0 that I can see is going to be an answer already. I just want to look for t's that are bigger than 0. So again, I'm going to do like what I did in the previous example, and I'll have t is greater than 0. I'm going to restrict where I look so that I'm only looking at positive values of t. So I hit enter, and I get this big nasty decimal. And do I want to work with that big nasty decimal? No, I don't want to have to write it down. So I'm going to plug this in to here and get my result by just using it. 1.66a, or I guess it's t in this case. We're going to evaluate at the t that I just found. Oops. I dropped a 6. So if I hit enter, I end up with negative 58. So here I get a negative 58 for my velocity, which makes sense because I'm heading down. I also know the symmetry of a parabola that opens down. When it hits the x-axis heading up, it's going to have the same velocity coming down, the same slope, both directions. Oops, didn't quite tip. Those will be same slope, just opposite in sign. And we've got to make sure we write down that time, which was 69.880 if we round 3 decimal accuracy and we put our units on. So you can work on your notes web exam problems, numbers 5 through 7, and then tomorrow come prepared to discuss how you decide whether you're finding time, velocity, or position in a particle motion problem and what you do in each of those scenarios.